All right, my name's Tom Smelker. I'm from Mercury Systems. Today I'm going to really ask a question to everyone. Is it really the end of Moore's Law? So I guess first I'd like to see a show of hands since it's a polarizing time in politics and this is a polarizing question. Who believes it's the end of Moore's Law? No one? Awesome. This is a great audience. Oh, a few. Okay, well, the few that said yes, I hope to sway you to the other side. And how we're going to do that is really through modular chip design, and that is what I'm going to be talking about. So I guess first of all, I'm the Vice President and General Manager of our Custom Microelectronics Solutions Group. So Moore's Law, back in 1965, 55 years ago, Gordon Moore said that we would continue to double the transistor size, transistors per chip, which is shrinking the transistors at a constant cost. And we did that to about 14 nanometer. And that was really an inflection point where we actually saw cost per transistor actually went up at that time. And so it's becoming more and more difficult to keep that exponential improvement going. So how are we going to do that? We're going to do that through heterogeneous computing. And actually, that's what Gordon said in his very last page. He's like, once the transistors get too small and we cannot innovate there, we're going to innovate through heterogeneous computing. So he got it right 55 years ago, and we're on that trend. Now, I'd say what you see here is in 2013, IEEE Spectrum said that we would continue down the path, but at a slower rate. And in 2015, I guess it was a very pessimistic year, really saw that no, we're going to actually stay stagnant. I would say what we're seeing is, 7 nanometers coming out, 5.5. We see trends to 5.5 and even 3.5. But at that point, you're not seeing that doubling of every 18 months like we saw for over 40 years. So so we're going to do it through heterogeneous computing. So if you look at how we've developed chips for the last 20 plus years, it's been ever expanding the capabilities and bringing more and more capabilities within the chip. So the CPU cores, the communications, the memories, adding GPUs and imaging, all the IOs, where, if you go back into the 90s, all of this was different BGAs on larger form factors, and we've continued to add the capability per chip. But then it gets expensive to, every time you port a capability or innovate to a new node, you have to port those technologies, and you also have to qualify those technologies, and some of them don't need to be at that advanced node. For instance, if you look at that, yes, you want your CPU cores and your GPUs at the leading edge, but not necessarily your memories or not necessarily your IOs or comms. And where we are today is, if you look at it, ever expanding size of die, every time you add a transistor, you add leakage current. So there's a swap cost there. So heterogeneous computing allows us to look at it in a modular way and be able to go back to the 90s almost with new technologies and be able to choose what chips and chiplets you want in a very small package on the same substrate. So using silicon interposers, we can right size the solution. I can choose the right CPUs. I can choose the right IOs. I can right size my memories. And if I need a graphics processor, I can add those. And if I don't, I don't need it. And it stays out of my system, and I'm not wasting that energy and that weight and that power and the size for it. And so that's where we're going. And that's where we see commercial industries trending, and that's where we see defense trending. And so what we're working on is trending that for defense. The value of modular chip design is even more than that. It's really being able to select what FPGA you want, what GPUs you want, what CPUs. Like I said, add the IO, the memories, other capabilities too, like a security chiplet, a chiplet focused just on AI or machine learning. And what's so exciting to me is directed digital convergence. So, high speed, high bandwidth ADCs all in the same chip. For the first time, we can actually have the high frequency chips sitting literally right next to your digital processors and be able to really shrink the swap of the entire processing chain. And so when you do that, we can now right size this for communications, signal intelligence, EW, radar, and many other applications. So that's how we're really going to keep Moore's Law moving forward. So, and it expands across all the different mission sets for defense and also for commercial too. So, Internet of Things, autonomous driving, the small sat, CubeSat, both commercial and defense, is all driving this path forward. So how are we solving it at Mercury? Well, we're solving it by doing exactly that, setting up an onshore capability where through trusted design, trusted manufacturing, we can partner with semiconductor industry and bring the chipsets and chiplets to the defense industry, integrate those for the specific mission set, solve that customer's problems, right size it for size, weight, and power, and deliver that in a very small form factor, smaller than a business card, much smaller than a business card. And what's very exciting is what used to take us at Mercury, a 3U card for the digital side, a 3U card for the analog size. We can now integrate both 3Us all into a very small package and save the customer a lot of swap, but also put the processing where it needs to be, right at the sensor edge. So I'd say, the traditional monolithic chip design, which I've designed lots of chips, and I'd like to say I could do it in 36 to 48 months. It's a lot tougher than that, but we can now, since we're not designing silicon and we're able to leverage silicon and chiplets from all these different capabilities, we can actually pull this off in 12 to 18 months and provide the capability and upgrade cycles that are badly needed. So with that, let's see. So an enabler here I did want to talk about that I forgot to is open systems architecture. Like the last briefing was talking about SOSA a lot. Well, what's going to enable this is having open systems architecture now at the chip scale. So where we're at today is, like I showed you, that inflection point where we're just starting to see chiplet design and the very first chiplets coming out. And so we have different standards, different interface standards for all these chiplets. So companies have to design to all these different standards if they want to get their chiplet to market. Where we'll need to go in the future is to have standards for chiplets so that we can rapidly integrate capabilities and drive innovation so that companies will invest in chiplets. Smart AI companies will invest in chiplets and be able to use them in signal intelligence, security, you name it. So that's really the next step to really get this fully moving forward. So with that, are there any questions?